NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams.
The James Webb Space Telescope had been watching silently from its vantage point beyond the moon's orbit, absorbing ancient light and peeling back the curtains of time, when it captured a revelation that shook even the most steadfast minds in cosmology. For decades, humanity's understanding of the universe's scale had been expanding bit by bit, like an ever-unfolding map. Each new telescope, from Galileo's rudimentary glass lenses to Hubble's eye in the void, had added new dimensions to this map. Yet none had redrawn it so radically as Webb just did. Its most recent observations revealed that the scale of the cosmos is far greater, far richer, and far older in complexity than even the boldest models had predicted. The images and data it returned were not just scientific achievements. They were revelations that pulled at the very foundation of what we thought the universe was. Before we start, smash the like and subscribe buttons for more updates. The heart of this breakthrough lay in the unprecedented clarity of Webb's infrared vision. Unlike visible light telescopes, Webb could pierce through thick veils of cosmic dust, seeing where starlight had been hidden for billions of years. When it turned its instruments toward deep fields, tiny, seemingly empty patches of sky, those dark voids lit up with galaxies, some so distant that their light had begun its journey mere hundreds of millions of years after the Big Bang. And yet, these galaxies were not the tiny, primitive clusters scientists expected. Instead, Webb found sprawling, mature galaxies, some as massive and organized as our Milky Way, existing at a time when the universe should have been in its chaotic infancy. This discovery forced an immediate reckoning with our understanding of cosmic growth. The prevailing models had suggested that galaxies grew slowly over billions of years, merging and accumulating matter gradually. What Webb revealed was a universe that had built immense, complex structures astonishingly quickly. This meant that either the early universe was far more efficient at creating order than predicted, or that our very timeline of cosmic events required revision. In either case, the scale of the universe, its complexity, its density of matter, and the speed at which it evolved had to be recalculated. Even more striking was the number of galaxies visible in Webb's deep field surveys. The telescope detected them in such abundance that the previously accepted estimate of around 2 trillion galaxies in the observable universe now seemed far too low. With its sharper eye, Webb could pick up faint and small galaxies that older instruments simply missed. If these faint galaxies were this common across the sky, the total number could be several times higher than previously imagined. This was not merely a matter of counting more galaxies. It was a recognition that the cosmic architecture itself was richer and more densely packed with matter and light than human science had dared to assume. Light from these distant objects had been traveling for over 13 billion years to reach Webb's mirrors, meaning the telescope was effectively a time machine, showing us the universe as it existed shortly after its birth. Yet paradoxically, what it showed us were not the expected embryonic forms of cosmic matter, but vast, established systems. Some of these galaxies seem to have undergone multiple generations of star formation, suggesting that they must have started forming stars at an almost inconceivably rapid pace. The chemistry of these galaxies also revealed heavier elements: carbon, oxygen, iron, elements forged in the hearts of stars and scattered by supernovae. Their presence in such young galaxies suggested a cycle of creation and destruction playing out far faster than standard cosmology had accounted for. This was more than a curiosity of astrophysics. It spoke to the deep physics that governed the universe itself. For these early galaxies to exist in such a state, either dark matter had played a far more influential role in shaping cosmic structures than models allowed, or there were unknown processes in the early universe that accelerated matter into complex forms. Some theorists began considering whether the expansion of the universe itself and the rate at which it cooled after the Big Bang might require adjustment. Others questioned whether we were missing key interactions between matter and energy in the primordial plasma, subtle physical laws that had eluded detection until now. The sheer visual beauty of Webb's images added an emotional dimension to this scientific upheaval. When astronomers released the first of these deep field images to the public, The scene was breathtaking. A tapestry of light and shadow, with galaxies in spirals, arcs, and clusters, some distorted into cosmic smears by the warping of space-time itself. Gravitational lensing, caused by massive clusters bending the path of light, acted as a magnifying glass, revealing even fainter and more distant galaxies behind them. In some cases, a single point of light represented a galaxy containing hundreds of billions of stars, all so far away that their combined glow was just a faint dot in Webb's frame. The implications stretched beyond astronomy into the philosophical. If the observable universe contained far more galaxies than thought, and if those galaxies were themselves forming stars and planets far earlier than expected, then the probability of life elsewhere shifted as well. Planets could have formed billions of years before our own sun existed, in galaxies that had already reached maturity while Earth's atoms were still floating in interstellar clouds. The cosmic timeline for life to emerge and evolve widened, suggesting that the universe could be teeming with civilizations at every conceivable stage of development, some impossibly ancient by our standards. Scientists working with Webb's data found themselves revisiting long-settled debates. The Hubble constant, measuring the rate of the universe's expansion, was already the subject of heated discussion, with different methods producing slightly different results. Webb's deep-time observations added new wrinkles, offering more precise distances to ancient galaxies, and potentially clarifying or complicating the tension between current measurements. If the expansion rate was different in the early universe than expected, that could have profound consequences for understanding the age and ultimate fate of the cosmos. Perhaps the most disorienting aspect of Webb's discovery was not the vastness of space, but the vastness of time. The human mind is not built to fully grasp billions of years, yet Webb's images compressed them into something almost tangible. Each photon captured was a messenger from a past so distant that our own species, our planet, and even our galaxy did not yet exist. This sense of temporal depth shifted perspective. The scale of the universe was not just about distances measured in light years, but about epochs stacked upon epochs, cosmic eras layered like geological strata, each one hiding its own mysteries. The scientific community quickly began to integrate these findings into simulations and theoretical models. Supercomputers ran updated calculations of galaxy formation, factoring in the denser, more active early universe that Webb had revealed. These simulations began to produce universes that looked more like Webb's images, crowded, luminous, and ancient-looking even in their youth. Yet these models still could not fully explain the rapid organization of matter, hinting that something fundamental remained undiscovered. For those who had spent careers studying the deep universe, Webb's revelations were both exhilarating and humbling. They confirmed that even with centuries of astronomical progress, humanity was still standing on the shoreline of a vast ocean, with the deepest waters still uncharted. The telescope's ability to detect light at such extreme distances made it clear that every observation would challenge some assumption. Every data set would rewrite part of the story. Webb's announcement of the true scale of the universe did not come as a single proclamation, but as a cascade of discoveries, each adding to the immensity of the picture. The scale was not merely linear, more light years, more galaxies, but structural and dynamic. The universe was larger in its contents, denser in its early stages, and more complex in its evolution than anyone had dared to model. That meant our place within it was even smaller and more fleeting than previously thought, yet also more extraordinary, as a conscious species capable of witnessing such immensity. One striking example from the data was a galaxy that appeared to be fully formed just 350 million years after the Big Bang. According to prior understanding, galaxies at that point in time should have been small, irregular, and in the earliest stages of assembly. Instead, this galaxy showed a spiral-like structure, evidence of a disk and even hints of ordered star populations. If galaxies could organize themselves to this degree so quickly, then cosmic structure formation was far more efficient, and possibly governed by physical laws we did not yet understand. Webb also captured glimpses of light from what might be some of the first generation of stars, known as Population 3 stars. These stars, forged from pristine hydrogen and helium with no heavier elements, had been theorized for decades but never directly observed. They would have burned hot and fast, seeding the universe with the first heavier elements necessary for planets and life. If Webb's data could confirm their existence, It would be a direct look at the moment the universe began to diversify its building blocks. That would add yet another layer to the universe's scale, not just in physical size, but in the diversity of its matter and the richness of its history. As the news spread, it was not only scientists who were moved. Artists, philosophers, and ordinary stargazers found inspiration in the realization that the universe was even more unfathomable than they had imagined. Some looked at Webb's images and saw an invitation to dream bigger, to imagine futures where humanity might one day reach out to these distant lights. Others felt a quiet humility, a recognition that our own dramas played out on a pale speck drifting in a vast ancient ocean. The event marked a turning point not because it closed questions, but because it opened so many new ones. Webb had not just measured the scale of the universe, it had redefined what that scale meant. No longer could scientists think of the early cosmos as a sparse, slowly organizing expanse. Instead, it was a place of rapid creation, of intense light and complexity, a fertile ground for galaxies to bloom almost as soon as the cosmic clock began ticking. With each new observation, the telescope continued to feed data that would take years to fully analyze. But even in these early stages, the core truth was unavoidable. The universe was bigger, older in structure, and more complex in its youth than humanity had dared to hope. The implications stretched across cosmology, particle physics, and even astrobiology, altering how we thought about everything from the birth of matter to the potential for life. And so, floating far from Earth in the quiet darkness of space, the James Webb Space Telescope continued its silent watch, gathering light that had traveled for billions of years, each photon carrying a fragment of the story. With its most recent revelation, it had not only expanded the boundaries of science, it had expanded the boundaries of imagination itself. The true scale of the universe was no longer a static number or a distant abstraction. It was a living, evolving reality, unfolding before our eyes in greater majesty and mystery than we had ever known. The James Webb Space Telescope's breakthrough on the scale of the universe had only just begun to ripple outward when teams around the globe shifted their focus to the instruments and methods that had made this revelation possible. While the world marveled at the images, astronomers, cosmologists, and physicists were equally captivated by the astonishing precision with which Webb had extracted light from across cosmic history. It was not simply a matter of pointing the telescope toward an empty part of the sky. It was the synergy between engineering, data analysis, and theoretical physics that allowed these faint ancient photons to tell their stories in such exquisite detail. Webb's architecture was built for exactly this kind of discovery. Its segmented primary mirror, composed of 18 gold-coated beryllium panels, was engineered to operate flawlessly in the frigid vacuum of space. Each segment was aligned with nanometer precision, creating a single massive mirror over 6.5 meters across. This immense surface area was crucial for collecting enough light from galaxies so faint that they were billions of times dimmer than the naked eye could see. Gold was chosen not for its color, but for its ability to reflect infrared light with remarkable efficiency, ensuring that even the most tenuous signals could be gathered and measured. The choice to make Webb an infrared telescope was fundamental to its ability to redefine the universe's scale. As the universe expands, light from distant galaxies is stretched or redshifted into longer wavelengths. The earliest light, born in the first hundreds of millions of years after the Big Bang, is now deep in the infrared part of the spectrum. Optical telescopes, like Hubble, are blind to much of this light, but Webb's instruments were designed to capture it in full. The near-infrared camera. NIRCam could detect structures in galaxies billions of light-years away, while the mid-infrared instrument MIRI penetrated even thicker clouds of dust, revealing star-forming regions hidden from all previous observatories. To achieve this sensitivity, Webb had to operate at temperatures just a few dozen degrees above absolute zero. This required one of the most ambitious engineering solutions in space exploration. A tennis court-sized sun shield, 5 layers thick, each thinner than a human hair. This shield permanently blocks sunlight and heat from Earth, allowing the telescope's instruments to cool naturally in the darkness of space. Without this extreme cold, the faint heat signatures of ancient galaxies would have been drowned out by the telescope's own warmth. These engineering triumphs were only part of the story. The true depth of Webb's data came from its capacity for prolonged exposure. Some of the images that reshaped our understanding of cosmic scale were the result of many hours of continuous observation on a single patch of sky. Each photon counted was a survivor of an unimaginably long journey, passing through the chaos of the young universe, through vast intergalactic voids, and finally into Webb's detectors. By layering exposure after exposure, the telescope built a signal strong enough to map the structure, composition, and distance of galaxies that had never before been detected. This clarity allowed scientists to make precise measurements of redshift, the key to unlocking cosmic distance and age. Using Webb's near-infrared spectrograph NIRSpec, astronomers could split the light from a galaxy into its constituent wavelengths, revealing not just its motion through space, but its chemical composition and star formation history. The higher the redshift, the further back in time we were looking. By capturing galaxies with redshifts well above 10, Webb extended our observational reach into an era previously considered invisible. With these tools, researchers began constructing an updated map of the universe's structure. The new scale did not simply mean more galaxies farther away. It meant that the universe had matured at an extraordinary pace. Galaxies that should have been small and irregular were already large, organized, and chemically enriched. Massive clusters, gravitationally binding hundreds or thousands of galaxies together, appeared far earlier than theory had suggested. These clusters, in turn, acted as cosmic lenses, bending light from even more distant sources into view. Webb was not only looking deeper, but using nature's own magnifying glasses to peer further still. The recalibration of the universe's scale required careful statistical analysis. Webb's survey fields were meticulously chosen to avoid bias, meaning they were placed in different parts of the sky to ensure the distribution of galaxies wasn't a local anomaly. Each deep field represented a window into the distant past, and comparing them allowed astronomers to estimate the overall density of galaxies across the sky. This density, multiplied across the entire celestial sphere, pushed the total number of galaxies upward, far beyond what earlier telescopes had hinted at. What was perhaps most revolutionary was that this new scale suggested a cosmos bursting with potential for complexity from the very start. If mature galaxies appeared so early, the environments in which stars and planets formed were established much sooner. This had cascading implications for the likelihood of life elsewhere. Planets orbiting stable stars could have emerged in these ancient systems, potentially giving rise to life long before Earth itself coalesced. For astrobiologists, this opened the door to considering civilizations that might predate humanity by billions of years. The shift in understanding also reached into the heart of cosmology's most challenging puzzles. The rapid formation of massive galaxies suggested that dark matter, the unseen scaffolding on which galaxies are built, might behave differently than current models predict. Perhaps it clumped more efficiently, pulling gas into dense regions where stars could form at extraordinary rates. Alternatively, the laws of physics governing the early universe might have been subtly different, allowing matter to cool and condense faster than expected. These possibilities were not merely theoretical diversions, they could reshape our grasp of the fundamental forces of nature. The early universe was governed by extreme conditions, where the interplay between gravity, radiation, and the quantum fields that underlie all matter determined the path of cosmic evolution. Webb's findings hinted that there might be gaps in our understanding of this interplay. Gaps that could lead to new physics beyond the standard models of cosmology and particle theory. Even the cosmic microwave background, the faint afterglow of the Big Bang, gained new context in light of Webb's data. Observations from missions like Planck had provided a detailed map of this ancient radiation, showing tiny fluctuations that seeded the large-scale structure of the universe. Webb's view of the fully formed galaxies that arose from those seeds offered a way to connect the earliest moments of the cosmos directly to the structures we see today. The consistency, or lack thereof, between these two pictures could confirm or challenge our models of how the universe expanded and cooled. The instruments aboard Webb also allowed scientists to examine the intergalactic medium, the thin gas between galaxies, with unprecedented precision. By studying how the light from distant quasars and galaxies was absorbed along its journey, they could map the distribution of matter across space. These measurements revealed filaments of gas stretching between galaxies, forming a vast cosmic web. The scale of this web, and its maturity in the early universe, was yet another reminder that cosmic structure emerged with astonishing speed. The detection of chemical signatures in these distant systems added another layer of intrigue. Heavy elements like oxygen, nitrogen, and iron are produced in stars and spread through space by supernova and stellar winds. Finding these elements in abundance so early in cosmic history suggested that star formation and death had been occurring at a furious pace from the start. This rapid chemical enrichment had direct implications for planet formation, since rocky worlds require these heavier elements to exist at all. Beyond the pure science, Webb's revelations also shifted the culture of exploration. Space agencies, universities, and research teams around the world began recalibrating their priorities. Missions once aimed at filling in small details of the cosmic story now had to grapple with a much larger, more complex narrative. The telescope's success underscored the value of long-term, high-risk, high-reward projects. Investments that could take decades to bear fruit, yet yield insights capable of rewriting textbooks. The international nature of Webb's mission also reinforced the importance of global collaboration. Its construction involved thousands of engineers, scientists, and technicians from multiple continents, and its operation now depended on an open exchange of data and ideas. This collaborative spirit was mirrored in the way discoveries were shared with the public. Images were released freely, allowing anyone, from professional astronomers to schoolchildren, to engage directly with the raw beauty of the cosmos. As more data poured in, it became clear that Webb's revelations were not isolated surprises, but part of a consistent pattern. Every deep look into the cosmos revealed more galaxies, more complexity, and more ancient structure than anticipated. The scale of the universe was not only larger than thought, it seemed to be richer in detail at every level of observation. Some researchers began to explore whether these findings could connect with other cosmic mysteries, such as the nature of dark energy, the force driving the acceleration of the universe's expansion. If the early universe was denser with galaxies, then the way that density thinned out over time could provide clues about how dark energy behaved in the past. This, in turn, could help predict the ultimate fate of the cosmos, whether it would expand forever, slow to a halt, or end in a catastrophic collapse. Webb's role in refining the cosmic distance ladder, the set of methods used to measure distances in space, was equally vital. By providing more accurate measurements of far-off galaxies, it allowed astronomers to cross-check and calibrate other techniques, from parallax to standard candles like Cepheid variables and type Ia supernovae. This, in turn, fed back into measurements of the Hubble constant, potentially resolving or deepening the existing tension between different methods. One of the subtler yet profound implications of Webb's discoveries was the shift in how humanity visualized time. For centuries, the night sky had been seen as a static dome, its stars unchanging across human lifetimes. Gradually, science had revealed that each point of light was a journey into the past. Webb made that past palpable. The galaxies it revealed were not just far away. They were snapshots of a living universe in different stages of growth. To look at them was to witness moments that had long since faded from the present, yet still existed in the form of ancient light. The announcement of the true scale of the universe thus became not just a scientific milestone, but a cultural and existential one. It reframed humanity's sense of place, suggesting that we inhabit a universe whose richness and depth may forever outstrip our capacity to fully comprehend it. And yet, rather than discouraging exploration, this realization ignited a deeper curiosity. If the cosmos could surprise us so profoundly now, what further wonders awaited as Webb continued to scan the sky? In the months following the initial revelations, plans were drawn to push Webb's instruments to their limits. Observations were scheduled to target the faintest, most distant smudges of light detected so far, in hopes of finding galaxies from even closer to the moment of cosmic dawn. Researchers also began using Webb to study galaxies in the Middle Ages of the universe, those forming a few billion years after the Big Bang, to trace the transition from the hyperactive early universe to the more sedate cosmic landscape of today. The telescope's versatility meant that while it was revolutionizing our understanding of the largest scales, it was also probing smaller structures in incredible detail. Star-forming nebulae, exoplanet atmospheres, and the dusty cores of nearby galaxies all came under its gaze, revealing the same richness and complexity that characterized the larger cosmic web. This multi-scale approach ensured that the story of the universe's scale was not just about how big it was, but about how deeply interconnected its structures were across all magnitudes. Every layer of discovery fed into the next. The identification of early chemically enriched galaxies pointed toward a universe where planets and potentially life could have formed almost as soon as it was physically possible. This suggested that the search for biosignatures, chemical markers of life, in exoplanet atmospheres might benefit from targeting older stellar populations in ancient galaxies. In a way, Webb's redefinition of scale also redefined the search for life, making it both more urgent and more expansive. The James Webb Space Telescope's announcement was not a final statement, but the opening chapter of a new era in astronomy. By revealing the true scale of the universe in such vivid and unexpected detail, it had not only expanded our knowledge, but expanded the horizon of what questions we could ask. Its instruments would continue to gather light from the edge of time, piece by piece, constructing a more complete portrait of the cosmos. One that, no matter how detailed, would always leave room for the next surprise just beyond the reach of our current vision. The revelation of the universe's true scale did more than shift the boundaries of cosmic maps. It also reshaped the ambitions of humanity's future in space. Webb's deep vision into the formative eras of the cosmos prompted an urgent reconsideration of where and how we might direct exploration in the decades to come. Space agencies began to view the telescope not just as an observatory, but as a pathfinder for the next generation of missions. Missions that could target newly identified structures, clusters, and planetary systems with unprecedented precision. Among the most immediate consequences of Webb's findings was the refinement of target selection for future deep space probes. While prior surveys had focused on relatively nearby galaxies for the search for habitable planets, Webb's catalog of mature ancient galaxies introduced a new category of interest: those that had stable environments billions of years earlier than the Milky Way. Such galaxies, if they harbored planets, could contain biospheres that had been evolving for time spans almost beyond imagination. The prospect of finding life not only out there, but potentially much older than here, became more than a speculative dream. It became a testable possibility. The broader astrophysical community responded by proposing coordinated studies that would link Webb's discoveries with the capabilities of other observatories. The Atacama Large Millimeter-Submillimeter Array ALMA, with its ability to study cold dust and molecular gas, could complement Webb's infrared data, revealing the raw material for star and planet formation in these ancient systems. Ground-based telescopes equipped with adaptive optics could follow up on specific galaxies, measuring their internal dynamics to determine how such complexity could have arisen so quickly. The synergy between instruments, each operating in different parts of the spectrum, promised a holistic understanding of cosmic evolution across time. Another avenue of exploration inspired by Webb's results lay in gravitational lensing. The phenomenon in which massive clusters bend light from background objects had been known for decades, but Webb's precision transformed it from a rare observational bonus into a deliberate investigative tool. By targeting specific lensing clusters, astronomers could magnify and resolve galaxies that would otherwise be invisible, reaching further toward the cosmic dawn than any single instrument could manage alone. These lensed systems could become natural laboratories for studying the earliest phases of galaxy and star formation at resolutions that defied the limits of telescope engineering. The study of dark matter also took on renewed urgency. The unexpectedly rapid emergence of galactic structures implied that dark matter might clump more efficiently than predicted, altering the gravitational landscape of the early universe. To test this, theorists began developing simulations that incorporated Webb's observations, adjusting parameters for dark matter particle properties and distribution. If these simulations could reproduce the telescope's findings, they would provide indirect evidence for the nature of dark matter itself, one of the most elusive components of the cosmos. Beyond its impact on physical science, Webb's announcement also spurred cultural and philosophical dialogue on an extraordinary scale. Philosophers, theologians, and historians joined scientists in discussions about what it meant for humanity to occupy a universe far more immense and ancient in its complexity than previously believed. For some, the revelation underscored the fragility and rarity of conscious life. For others, it reinforced the idea that life, given the sheer scale and variety of cosmic environments, might be a natural consequence of the universe's unfolding. The expansion of scale reframed the Fermi paradox in striking terms. In a cosmos with so much time and space for civilizations to arise, the silence we currently perceive became even more profound and more puzzling. Educators seized on Webb's imagery as a transformative teaching tool. The telescope's portraits of ancient galaxies were not abstract numbers in a textbook, but vivid, almost tangible visions of history. Students could trace light across billions of years, watching the universe transition from its turbulent youth to its structured maturity. The effect on public engagement was dramatic, with astronomy clubs, planetariums, and online forums experiencing surges of interest from people eager to understand the new cosmic map. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the James Webb discovery about the universe's true scale? We want to hear from you. Thank you for watching, and see you next time.